Okay, let's start with some bad news. My milling of aluminum is not going fantastically. As you can see, I have an absolute shit, like it's rough, an absolute shit surface finish. I also have an absolutely abysmal side surface finish. My chips are welding to not just the surface, as you can see here, but also the cutter. This is not off to a good start, and I don't think it's very promising because this was already trashed material, and thankfully aluminum 6061 is cheap and plentiful, but because it's already trashed, I've been using it to try different feeds and speeds. But as you can see, no matter what I do, I get absolutely trash finishes on both the face and the sides of cuts. So I need to completely rethink my strategy here. This is not going to work. So let's talk about what I've done and where I think I need to go. I'm not going to bother showing you what I've done because you can obviously see there's nothing to be learned from it besides it didn't work. But let's talk about what I did try. Everyone that I've seen successfully milling parts out of aluminum on desktop style CNCs, router CNCs, not CNC mills, but hobby CNCs, recommends using single flute, a lot of times O flute cutters. The reason that they recommend single flute cutters for aluminum on these types of non-mill CNC router machines, these hobby machines or machines optimized for woodwork, is because they operate at higher RPMs than, say, a metal mill. And because of that, you would have to run at extremely fast feed rates in order to have proper chip load if you had more than one flute going on here. 2 flutes, God forbid, 3 flutes, 4 flutes. So because of that, people recommend using these single flute cutters so that you can run at reasonable feed rates while still adhering to the optimal RPM band that these spindles and routers are able to give you proper torque at and not ruin their bearings. Here's what I'm learning. I also tried a 2 flute bit. I don't want to go this route because it's going to not be able to have the chip load that I would want for optimal performance, and it will wear these bits faster than I would like. These are both Onsrud bits, and they are not cheap. I actually broke the up cut version of this O flute. That's like, what, $40? Didn't feel good. But I did get a better finish on the surface, not necessarily on the side, but on the surface, using the 2 flute bit. The research that I've done points to my problems likely being from vibration. This is how I have it held down. There's index pins in these 2 holes, so I can properly index it to the table, and then I have hold downs, and then for some operations I was also holding it in the middle, like when I was just working up here. It didn't make any difference. I think what's going on here is the combination of aluminum and a large bit is just not going to work on this machine. And by large bit, I mean a 1/4 inch diameter and up, maybe even 3/16. I don't know, I haven't tried that. I think also, from what I've been reading, these single flute bits are not balanced because they are not symmetrical. And so when you spin a single flute bit, it's causing more vibration than, say, a double flute bit, which is perfectly symmetrical. And the bigger you get the bits, the more vibration that is going to impart on your machine, and the worse the surface you're going to get is. Okay, so what are we going to try in order to fix this? Well, first things first, we're going to flip this around, and I'm going to try milling on this end that we haven't touched yet. I'm not going to break out a new piece and waste material, but we are going to try that with a smaller single flute bit. If you saw my previous videos on modifying AR-15 aluminum lowers, you'll know that I've had no problems with small bits. 16th inch bits, 1/8 inch bits, heck, even 2 flute 1/4 inch bits for roughing not for finishing though. So I'm going to go with the hypothesis that these are just too big for this machine in this material, and we are going to work our way down to 1/8 of an inch, just cheap Amazon bit to try out. If that doesn't help, we are going to try and introduce a different method of chip clearing. We are going to look at blasting air to clear chips. And if that doesn't help, we are going to look at potentially introducing some coolant. I'll be honest, I don't have high hopes for this, mainly because during the 1/4-inch tests, I was using a vacuum for chip clearance, and also I tried it with and without coolant, both WD-40 for cutting and someone suggested alcohol. Neither of those made any difference. So I really don't have high hopes for this, and this seems like a pain to hook up anyways. So hopefully this gives us results that we like. All right, we're going to do a quick test. I did a little tiny cut there. I think this feed and speed that I got from a review on Amazon of this bit may be promising. I'll tell you the details of it if it works in a larger test. But let's run a pattern here to see if we can't face off some of this material for a 1/16 of an inch drop down. That speed and feed definitely worked. The finish is fantastic. I didn't see or hear a lot of vibration. Best I can tell from the really shallow depth of cut, that side looks good too. I stopped it because I was happy with the result. The other thing I wasn't happy with is that's going to take forever to do a big piece like this, or really anything. So I'm going to now double the depth of cut, double the step over from what it was on that test, and see if that does anything. Just to let you know what it is right now, the depth of cut is 16 thousandths of an inch with a 10% step over at 16,000 RPMs with an 18 inch per minute feed rate. So what I'm going to do is I'm going to double that depth of cut up, and we are going to do 32,000 steps of depth of cut with a 20% step over. So no change to RPM, no change to feed rate, just depth of cut and step over. And I'm going to rerun that path. One thing to keep in mind is that it's only going to be doing a single X of depth of cut where we've already cut, because I didn't change the profile or start depth or anything like that. It's only when we get out to that little bit that was left at the edges that I stopped it before it could do, where we're actually going to see how it's going to handle that double depth of cut. But we should be seeing in this section how it handles the 20% step over. So for the first level, except for when we got to the edges, it was doing double the step over at 20% from our first test, and it was doing a single 16th thou depth of the cut. I felt it while it was running, and I really liked the surface. Just when it was over here, I would touch it. Really nice surface. And then when it went to the next depth, it did the full 32nd of an inch depth of cut while doing 20% step over. I still really am happy with that surface. You can't feel anything, and so that'll sandblast out just fine, except maybe one spot, and we'll talk about that in a second. And then if I look at an angle and I look at the side here where it cut, I do see a little chatter, but again, I don't think it's anything that will, oh my cut myself, but because aluminum can be sharp. But I don't think it's anything that bothers me. I can always do an onion skin pass of all visible edges if necessary to just kind of finish that up nicely. I'm really happy with this. I'm sure we can push it even more if we want to do more tests because it's really promising. Like I said, there's one spot where I can feel a little bit of something, and that's right here on this diagonal. And that's where the bit would come in and then go into the corner to widen out for the next round. That's going to be a problem for anything where you're using traditional tool paths like those available in woodworking CAM software for any sort of pattern, in this case, a facing pattern. I am in the process of teaching myself Fusion 360, which if you don't make any money off of it, like I don't, it is free for hobby use. The reason I'm doing that is Fusion 360 is optimized for metal milling, and they have a type of toolpath called adaptive clearing paths. And what that does is it makes sure that the lateral, they use another word for it, I think it's axial load on your bit is kept constant, and so therefore it doesn't jam it into corners where you go from only a portion of your bit being touching material at a time to like over half the bit touching material because it's jamming into a corner. That's what's causing that vibration there. Again, I don't think it's enough to actually not sandblast out, but if we can avoid it with technology, I am in the process of learning that technology so we can do that. Let's try some profiles. We are now going to do the front edge profile here. We are going to use the exact same settings that we used for the bit previously when doing our facing. Let's give it a go. Although it's going through spots that I already cut in the other direction and scrap at this point. I do like the side finish. I think that's completely usable. I only went down to 1/8 of an inch total depth of cut just to do this test. I will run a deeper version of this off camera so you can get a better idea of how it's going to behave when we get deeper. The only places that I'm really worried about that is in this channel here and over here, which you can't see, where it's kind of going in a little bit as well. If it leads to problems in bound channels like that, I think there's two solutions that we could go with, because again, I really like the results that I'm getting. Solution one is you could actually not program this as a profile. You could basically have your profile line and then have it come out and like bound it as like another place that you face the entire thing, and that way you're working up to your edge, and so it takes out all of that junk there and anything that would cause it to be in a bound channel at all. The other way to do that is very similarly, but done in a more automatic manner and with constant axial load, is again, I'm learning Fusion 360, and I could use adaptive clearing paths to make sure that it doesn't go into bound channels like that and it keeps a constant load. Both of those are viable strategies, but because this bit is dirt cheap, I'm going to continue plowing all the way down to the depth that I would need to cut for the actual final piece, which is, you can see this ledge down here. That's the final depth before we flip it over, and let's see what happens in that channel. This cheap little bit handled a total of 0.3 inches of depth of cut, not depth of cut, but a total of 0.3 inches cut pretty decently. Something happened on the last, I'm going to hazard a guess, 2 cuts or 2 levels. There's a slight, I can feel something with my finger, and you can kind of see a line there where it seems to have either cut differently or jumped out a little bit, or something happened. I don't know what, but I don't think that is the end of the world. If I look into the channels, the bound channel areas here, here, and here where it does the ramp down for the cut, I don't love the edge on the inside here or the outside here, based on how it's spinning and where it's traveling. That would be from the same reason. Again, I think doing adaptive clearing paths would help that. I also think that perhaps doing that sort of big clearing but not adaptive strategy I talked about would alleviate that. It's truly because it's being bound in these areas, and so there's just a lot more friction. I am going to look at installing this thing. It was cheap off eBay. I'm probably not going to go ahead and use coolant because it doesn't seem to need it from what I'm seeing. But I do think chip clearing with blasted air, which is half of that equation, will help out with some of this work going on. All in all, very promising. The only thing that I will say about all these experiments is these parts are going to take a really long time to cut at these rates. I mean, it is what it is. This is not a machine optimized towards metal cutting, so I'm glad that I'm just able to at all. But while doable, it's going to take a long time. The other thing that I will be a little worried about, and I need to check the depth of cut potential of these bits and probably try some even deeper cuts than this, but I am a little worried that I'm going to run out of stability and or depth of cut when doing the brackets that attach these legs to the actual handguard. But one problem at a time. Let's get some legs done. I went to go start a second trial, and I immediately screwed up by not re-zeroing my Z-axis and plunging the bit directly through 3/8 of an inch of aluminum at jog speed. But this presented me with yet another trashed piece that I can learn on, so I'm going to just go ahead and continue building it anyways, and I'm going to be using the bit that plunged through, because as you can see, the surface is still fantastic. All of that, I'm pretty confident, will blast out. And my sides look fantastic too. I did use the strategy where I'm taking the edge as if it were a pocket, so my outside line is like here, and it just progressively, so it doesn't leave those deep channels. Now, in some spots, it still goes through a channel. It doesn't clear out before it hits the edges, but whatever, at least it's not a deep channel. The other thing I will say is, my God, this is glacially slow. So I'm actually about to double the feed rate to 36 inches per minute, and then I'm going to do the rest. So we're at a 1/8 of an inch deep now, and we've got 0.3 of total depth to go. So we'll be able to tell if that doubling of the feed rate makes any difference, at least on the profile. There is essentially no difference in the surface quality from when we had essentially a chip load of 1 thou and doubled it to a chip load of 2 thou. I might be inclined at some point to try and triple it to a chip load of 3 thou, so add another 18 inches per minute to our now 36 inch per minute feed rate. But just at 36 inches per minute instead, it was much less infuriating to watch this cut. It is still slow. It is still going to take several hours per leg to mill, if this is any indication, but it is definitely doable, and I'm liking the results. All right, this is the last set of paths that I used the 1/8 of an inch bit with. I went ahead and did all of my through holes. They don't look like they're through holes yet because I'm going to pull a 1/16 of an inch off, or a little more than that, off the back. But those two are through holes. And then I also went ahead and I roughed out my decorative sort of recesses with the 1/8 of an inch bit as well. I left a floor of 10 thou and a wall thickness of 10 thou so that I can come back in with my 1/16 of an inch bit and just do that in a final finishing path for all of my stuff. I'm going to do a little cleanup of where I had some mistakes in my programming, but other than that, at least for this bit on this side, we're done. And there is the result of our 2-flute 1/16 of an inch bit doing its job and finishing up all of those pockets. I was a little concerned with it taking not only the last 10,000ths of an inch off the bottom, but also a full 1/16 of an inch depth of cut at the outsides of the pocket, where it was getting rid of that last 10,000ths of an inch of onion skin. But it took it like a champion. Again, this was a 2-flute because that's simply all I have in that size, but I will put the feeds and speeds down below. Here is the 2-flute 90-degree V-bit that I'm going to be using. The way that I'm going to strategize with this is I'm going to actually run it with an offset outside so the tip isn't cutting. The tip will be kind of floating in air a little bit off. And I'm going to start by just using, I'm going to pretend like this is an 1/8 of an inch end mill and see how that works out for us. Yeah, nope. Let's try same chip load as a 1/8 inch bit since this has got 2 flutes, but that is really bad. Now we're talking. I just ran it at 72 inches per minute and a very small, just 10 thou depth of cut, and it looks much better. I'm going to try it with that feed rate, but twice that depth of cut at 20 thou per cut. As you can see, it's not welding any chips on, but there's definitely not the smoothness of surface that I would desire. But we are getting closer. I think the depth of cut was fine at 10 thou. I'm just going to run it at that and see how it likes it. I just ran it at a chip load of 3 thousandths, which is a 96 inch per minute feed rate, and the surface, although not perfect, is much better. So this bit just likes being run aggressively. That's definitely the way to go, is push this thing. I'm definitely going to have some hand work that I'm going to have to do as well, just sanding, filing, whatever, to get this clean. But that seems to be about as clean as I can get it with what I've tried. I also had some stupidity. I tried to clean up that ledge and ended up going deeper than the angle on that bit, so now I have a flat section. I'll have to hand file that as well, but I also have some sections that I'll probably hand file to smooth out some connections between things as well. So it is what it is, and good thing this was a test. But what I did learn is all the stuff I needed in order to do these legs correctly. I also realized that when I do the facing operation on the back and leave the little nub that I've designed in, that's my positive indicator into the bracket, and the chamfering in the back, I need to do that first. And the reason being is, now that I'm at this point where I'm ready to flip it over and do the back, I'm realizing that the minute that I sever this last 70 thousandths or so of an inch that's connecting things, this is the only side that still has a full thickness face. Everything else is gone. So again, the minute that I sever this section and this section, this thing's going to fall out, and that'll stay flat, but this will fall downwards, and I am screwed. So I need to completely change my order of operations to do the back first, flip, and then do the front. Or if I did want to finish this one, I would have to buy some sort of vise that I could hold this with right about there and do the back operation. But I don't feel like buying a vise just to finish this trash leg. So I will pull this off of the CNC, and I will go and sandblast this just to see and make sure where my problem areas are. Obviously I know that some of my chamfers will need some hand work, but hopefully nothing else does. Here we go. Here are the results after sandblasting, and as you can see, I do still see texture on the area that we faced, so that's not good enough. If you watched my videos on AR-15 lightning cuts, you know I've had issues with the floor of inlaid areas not being the cleanest. Oddly enough, these two look clean, but that one has some texture. Now, this is less texture than I've seen on some actual professional products out of companies, sadly, but not good enough for me. But we know that the formula we're using is fine because these two are good, and that's closer to the clamp, so I'm thinking maybe it's a vibration issue. Also, we've got a nice floor on that inlaid area there. The bevel's actually blasted out just fine, except up here for some reason, even though that's the same bit that did these two larger sections. So I don't know what that's about. But what was definitely a problem is I didn't set the offset enough, because at corners, even with a couple thousandths offset like I discussed, it's peeling over, for lack of a better term, that edge instead of cutting it off. You can see what I'm talking about. And that will either have to be remedied in how we cut these, or I'm gonna have to do some hand filing or sanding to get rid of those, or get one of those tools where it kind of scrapes off, but that won't leave a nice edge. So I will probably, just for this test, even though it's gonna be garbage, I will probably hand file a little bit and see what it takes to get rid of some of these marks. I'll probably attack it with a file for the edges, and then this flat section here, I'll probably just hit with some 320 or maybe 220 and then 320 grit sandpaper and see if we can't improve things, blast it again. But most of the paths and strategies I believe are viable based on this result. I ended up sanding with a flat sanding block on the surface here with 220 grit and then 320 grit. That came out perfectly with very little work. So it's completely viable to get out machining marks from your facing operations using sandpaper. What didn't turn out so well is trying to modify my facets with files and or sandpaper. You can see here that my facets no longer perfectly line up. Is that the end of the world? No. Is that optimal? Also no. So what I would recommend is, I do think it's completely viable to cut out parts like this on a hobby CNC like mine. I think you've got to be okay with a little imperfection. The surface on some of those facets, like I said, I would offset it further so that the tip is running outside a little more to not leave that curl over edge that requires you to come in and fix things by hand. But even with that, the surfaces on the facets that I didn't touch are also not perfect. They're decent, but they're not perfect. And any place that I tried to really get into a corner and fix things, quote unquote, I just made stuff worse. So try and get your facets as close to perfect as possible directly off the machine. Fixing them is difficult at best. I would advise against it. But I think either you're gonna have to play around with feeds and speeds and more rigid holding, maybe do one side at a time and hold in multiple places to get perfect facets, or just be okay with a little bit of imperfection. It would be minor. Like I said, the best way to potentially solve this problem is to actually mill the back first and then have a hole on my spoil board that the little nub that we're gonna leave on the back can go down into, and then I mill the front. Obviously that's too late on this one, but again, this one is scrap. I'm gonna have to do both legs all over again. But I still am gonna continue my learning using this scrap. So there's two other ways that I thought of to deal with this problem. One of them would be to find a piece of material the exact same thickness as the drop from this face to this face, so that I could keep this up, hold it down, and probably mill it in sections so I can move clamps around to make sure that nothing sketchy happens. The other thing that I could do is I have been itching to try out my Saunders Machine Works mod vise. There's a bunch of cheap vices out there on Amazon, but the problem with them is they're not only cheap, they're cheap quality. If I was going to pay some money for a vise, I wanted something that was at least some quality and I could trust the mechanics of. These are only $100, which is a pretty dang good deal in my book. I'm going to have to remove my spoil board and attach them using the T-slots on my aluminum table underneath my spoil board, but that's fine. I'm happy to do that. And what this is going to allow me to do is I'm going to clamp it in this mod vise, and that's going to allow me to mill away the back and leave my little nub for our bracket. I'm also going to have to find a way to find where my different edges are. I will probably just do that using a wiggler. If you don't know what a wiggler is, just go look one up. And the cool thing about this is these jaws only let the piece sit down into the jaws a little bit. So I've actually got a gap between the material that I need to mill off and where my jaws are. So I'm also not risking screwing anything up. So this is how I'm going to finish this one. And then if I like it, I'm going to use this technique to do the two real legs, or maybe I'll do the hole in the spoil board method. The other thing that I am going to do is I am going to redo all of my paths using my Fusion 360 model. And the reason for that is not necessarily because I didn't like the result. The result's actually pretty dang good. Fusion 360 allows me to do my paths with these chamfers in such a way that I can control the angle that the chamfer goes out at. So the way it comes in, I can say 90 degrees, I can say 45 degrees, etc. What that's going to do is it's going to allow me to exit here and enter over here at a precise degree so that I can get my chamfer all the way into that corner and not worry about screwing it up by trying to fix it by hand.